In this video, we'll discuss properties of sine, cosine, and tangent. We'll start by defining these three functions. If theta is an angle in standard position, and p is a point on the unit circle that corresponds to the terminal side of that angle, we define sine as the y-coordinate, cosine as the x-coordinate, and tangent as the ratio between the y and the x. One question that we'll consider in order to understand these three new functions is, how are sine and cosine related? This question can be understood through an example. Say you were asked to find sine of theta given that theta was an acute angle and cosine was equal to 3/5. In order to solve this, you might draw a triangle. A right triangle with the angle theta marked here, and since cosine is adjacent over hypotenuse, you could put a 3 here and a 5 here. And you could quickly figure out that the missing height here, 3 squared plus y squared equals 5 squared, according to Pythagoras, would know y was equal to 4. And therefore, the sine, which is just opposite over hypotenuse, would be equal to 4/5. Another way to look at this problem, though, is through a property of sine and cosine. This property is also often called a Pythagorean identity because of its familiarity with the Pythagorean theorem. So using this property to solve the same problem, all I'd have to do is plug in 3/5, the known cosine value, and square it, and then, of course, subtract it from 1, and I would have sine squared of theta. So what I notice is sine squared of theta here would be 1 minus 9/25, or sine squared is equal to 16/25. And of course, that tells me that sine is equal to plus or minus 4/5. And that shows us why it was important for us to know that theta initially was in quadrant 1. That's how I know that the positive 4/5 was the sine ratio that I was after. This question of whether or not to use the Pythagorean identity or just the Pythagorean theorem to solve one of these problems really comes down to whether or not a coordinate is on the unit circle. In this example, we'll address that question exactly. We have an angle theta that terminates at the point 7/25, comma 24/25, and we want to know whether or not this point is on the unit circle. This is just a question of what's the radius. If I work out x squared, the x-coordinate squared plus y squared, am I going to get 1 or not? Well, that's pretty easy to figure. If I do 7/25 and square it, and then 24/25 squared, I'm going to get 49/6/25 plus 576 6/25. And sure enough, that is equal to 625 out of 625, or 1. So the answer is yes, that coordinate is on the unit circle. Knowing that a point is on the unit circle can be really helpful because, as you see in an example like this angle terminates at a point on the unit circle, and I can quickly identify that the sine of the angle is just the y-coordinate, the cosine is just the x-coordinate, and then the tangent is just the ratio that I get when I divide sine by cosine, so 24/7, without too much arithmetic to do. I can also quickly figure out that theta is the inverse tan of 24/7, which is about 1.28, 1.29 radians. And I would do something like that using my calculator, using the inverse tan key. So just to quickly expand upon that definition that we gave right at the very beginning, if theta is an angle in standard position that terminates at a point x, y, independent of whether or not we know that that point is on the unit circle, we can write that x squared plus y squared is equal to r squared and define sine, cosine, and tangent, as you see right here. One last example on this before we move on to some other properties of sine and cosine. If we know that an angle terminates at the point 5, 12, clearly that's not on the unit circle, but we could write that 5 squared plus 12 squared is equal to the radius squared, and therefore 25 plus 144 is the square of our radius. So we know that our radius is 13, and therefore the sine of the angle is 12/13, cosine of the angle is 5/13, and tangent of the angle is 12/5 y over x. Likewise, if we want to find the angle, we can use the inverse tan feature on our calculator. Sometimes that's called arctan rather than tan inverse. And inverse tan of 12/5 will give you about 1.18 radians. For a quick summary of the video up to this point, we can use x and y coordinates to tell us cosine and sine values when we're on the unit circle, and in other cases, we just write ratios to find the sine and the cosine. Let's start to take a look at some different properties of sine and cosine. Imagine theta were an angle on the unit circle. P is a point, and it corresponds to theta. The question is, what are the coordinates for an angle of negative theta? So maybe my angle theta might look something like this, and it terminates at the point x comma y. The big question is what happens if we ran that angle in the reverse direction, running it clockwise rather than counterclockwise. And it's pretty easy to see from the diagram here that the x-coordinate would remain the same. However, this y-coordinate is going to change sign. And this tells us something very important about sine and cosine of positive and negative angles. What we can see is that for every angle theta, sine of negative theta is equal to negative sine theta. Meanwhile, cosine of negative theta is equal to cosine of theta. That is to say that sine is an odd function, and cosine is an even function. At this point, you might be wondering, what happened to tangent? We haven't talked much about tangent so far in this video. If I'd like to know whether tangent was even or odd, I could simply use the definition. Tan of any angle is sine of that angle over cosine of that angle. Okay? And since sine is odd, I can pull this negative out. And since cosine is even, I can simply disregard the negative. And you can see in the end result, I get the opposite of tangent, which tells me that tangent is odd. Here we're told that theta is an angle and P is a point on the unit circle that corresponds to the angle theta. And we're asked to determine the coordinates of pi minus theta. So this time I'm going to picture my angle theta right here in quadrant 1, just like before. Just like this, that, and then the angle pi minus theta. So I would create that by traveling the same arc length here, but starting at this point here, pi, 180 degrees. And I'd be going in the reverse, the clockwise direction, since I'm subtracting theta. And you can see you're going to end up right about here, maybe about there. And we're speaking about this angle. This is the angle pi minus theta, if the angle drawn in black is the angle theta. And you can see the relationship, again, between the coordinates. X comma y, and now pi minus theta would have coordinates negative x comma y. So this time we see the x is changing sign, but the y is not. If I ask that question slightly differently, but instead the coordinates for an angle of 2 pi minus theta, the diagram would be similar. You'd start with an angle theta that terminates at some point x, y, But instead, you would finish up and think about 2 pi, 360 degrees, minus that same arc length. And you would end up at a coordinate maybe down here. We'd be looking at this angle, 2 pi minus theta. And you can see that the x-coordinate is the same, but the y-coordinate is opposite. And these questions just relate directly to properties of sine and cosine. I'll share them with you now. We can say for every angle theta, sine of pi minus theta, the y-coordinate, is equal to sine of theta. If I asked that same question for cosine, you could write a similar result, but the cosine would change signs. You could put the minus on the left or the minus on the right there. Meanwhile, cosine of 2 minus theta, now we're talking x-coordinate, that's equal to cosine theta. If I asked the same thing about sine, we could write it like this. And again, the negative could go on the left or the right. Knowing these properties of sine and cosine is really, really valuable information. If you were asked, well, what about tangent? Tangent of pi minus theta, how would that work out? Again, you could just fall back on tangent being the sine of an angle over cosine of the angle. Then you could refer to your properties on sine and cosine. Sine of pi minus theta is the same as sine of theta, whereas cosine of pi minus theta is the opposite, and therefore tan of pi minus theta is equal to negative tan of theta. So knowing a few properties for sine and cosine can extend a long way. With all this talk about properties, you might still be wondering, why did they come up with these silly names, sine and cosine, to begin with? There's actually a property that answers that question. Consider this. We know that sine of pi over 4 and cosine of pi over 4 are the same. So if you think in degrees, then sine of 45 degrees and cosine of 45 degrees, they're both root 2 over 2. Meanwhile, sine of 60 degrees is the same as cosine of 30 degrees, and vice versa. Can we generalize this? Can we figure out how sine and cosine are sort of directly related based on different but relatable angles? And maybe in such a way that we could find a cosine value that's equivalent to sine of pi over 9. Well, to answer this question, again, I'll draw a triangle like we did at the very first example. So here's my triangle. So sine of pi over 9 isn't a value that I've memorized or anything like that. It's certainly, I could work it out based off the unit circle, but I can also picture it this way. Since pi over 9 in radians multiplied by 180 over pi gives me 20 degrees, I can think about the sine of pi over 9 as being this height here, the opposite, over this hypotenuse here, or radius r. And so sine of 20 degrees is y over r. Well, it just so happens that if I turn my head ever so slightly and focused on this angle up here, which happens to be equal to 70 degrees, 70-degree angle here, and I asked myself about the cosine of that angle, cosine of 70 degrees, I see that the adjacent side to the 70-degree angle is y, and the hypotenuse is still r. So cosine of 70 is the same as sine of 20. Sine of 20 is equal to cosine of 70. And that is to say that sine of pi over 9 is equal to cosine of, if you take 70 degrees and convert it to radians, you get 7 pi over 18. So what is it, in fact, with 20 and 70? With pi over 9 and 7 pi over 18, well, it's pretty simple. These two angles in any right triangle are going to be complementary. 20 plus 70 equals 90. And the fact that they're complementary angles gives us our next property. For every single angle theta, sine of theta is equal to cosine of 90 degrees minus theta. So I'll note here that theta and pi over 2 minus theta, these are complementary angles. Complementary angles sum to 90 degrees, right? And this is exactly how sine and cosine get their name. Cosine is the ratio of sine's complementary angle. Of course, you can write this property in reverse. Sine of 90 minus theta is equal to cosine of theta. You might wonder if tangent has a complementary function as well. We will be getting to that soon. But first, some other properties. A function is called periodic if there exists some positive number p such that whenever theta is in the domain of f, so is theta plus p. And it's true that f of theta is equal to f of theta plus p. Now, this is just a fancy way to say that a function is called periodic if it repeats every so often. And we know that sine and cosine do. They repeat every 2 pi radians, or 360 degrees. So in the case of the sine and the cosine function, the period, this p-value, is 2 pi. But what about tangent? If we know that sine repeats every 2 pi, and cosine repeats every 2 pi, does that automatically mean that tangent repeats every 2 pi? To answer that question, let's consider a different question, or rather a different property. We've already seen that sine is the y-coordinate, and therefore it's positive in quadrant 1 and quadrant 2, while it's negative in quadrant 3 and quadrant 4. Meanwhile, cosine is the x-coordinate, making it positive in quadrant 1 and quadrant 4 and negative in the others. If we look at tangent, the question with tangent is, where is it positive? Well, we know that tangent is the ratio of sine to cosine. So when sine and cosine are both positive, tangent will be positive. However, if sine and cosine are both negative, then their ratio will still be positive. So tangent's also positive down here. Meanwhile, if sine is positive and cosine's negative, or vice versa, here and here, there I'd see my tangent is less than 0. So remember, ultimately, the question was, how long does it take before tangent repeats itself? What was its period? So sine, it goes positive, positive, negative, negative. It doesn't do a full cycle until we get all the way around the circle. Likewise with cosine. Positive, negative, negative, positive. Then it starts to repeat itself. But tangent, the repetition happens a lot sooner. Positive, negative, oh, already repeating, positive and negative. This also is consistent if you think about tangent as the slope of the line formed by the origin and the terminal point on the angle. So that means the period for tangent is just pi and not 2 pi. This also reminds me of a helpful mnemonic to remember where sine and cosine and tangent are positive and negative. ASTC. For years, many teachers would teach the mnemonic. All students take calculus as a way to say that in quadrant 1, all 3, sine, cosine, and tangent are positive. All are positive. And then in quadrant 2, only sine is positive. Student starts with S. And then in quadrant 3, only tangent is positive, while in quadrant 4, only cosine is positive. I always preferred some variation on that, like all shucks the cops, which I think was Mr. Feeney original, or even something more random and strange, like all squirrels tickle chickens. You can come up with your own mnemonic, but it's really as easy as remembering that sine is the y-coordinate and cosine is the x-coordinate. Using that idea, we could determine the quadrant where the terminal side of an angle lies, given some basic information. If sine is positive and cosine is negative, that implies that the y is positive, so it means I gotta be up here somewhere. Meanwhile, the x is negative, so I have to be over here somewhere. and therefore I'm in quadrant 2. Meanwhile, if tangent is negative and sine is negative, now I know that the y-coordinate is definitely negative, but I also know that the ratio of the y to the x is negative, and that tells me that the x is indeed positive. So I'm over here somewhere, or if you prefer, you could say the slope's negative, which means I'm over here somewhere. Either way, the overlap is happening down here in quadrant 4. You'll see that these kind of questions are actually super important because they're going to help us with our last example. So here I'm given that tangent is root 3 over 3, and I know that cosine is negative. I want to find cosine and sine. So assuming that you haven't memorized the values of tangent, I'm going to say that the y is root 3 and the x is 3. Because tangent is y over x. However, I automatically notice that there's something wrong with this situation because I'm told that cosine is less than 0. And so that must mean that x is equal to negative 3. However, if x is equal to negative 3, I have another problem because then y divided by x wouldn't be a negative. Wouldn't be a positive. So it must be the case that y is also a negative. One way to avoid this kind of difficulty in the beginning is I see that tangent is a positive value, so I know I'm in either this quadrant or this quadrant, and I know that cosine is a negative value, and thus I'm either here or here. And now I can say right away, before I get any further in the problem, that I'm in quadrant 3. And in quadrant 3, y's are negative, and so are x's. Right? And now I can proceed with the problem as I normally would. I need to know sine and cosine. Sine is not root 3, and cosine is not negative 3. I need to calculate the radius. So r squared is x squared plus y squared. So r squared is equal to negative 3 squared plus negative root 3 squared. And so r squared is 9 plus 3, which means r is the square root of 12. The radius is always positive. Square root of 12 can be simplified as 2 root 3, and therefore the sine is my y-coordinate right here, negative root 3, divided by my radius, 2 root 3. And that simplifies to just negative 1/2. Meanwhile, cosine is just my x-coordinate, negative 3, divided by, once again, my radius, which is 2 root 3. And when you rationalize the denominator, you get negative root 3 over 2. To summarize all this, there are many, many useful properties of sine and cosine, and this is just the beginning. Rather than memorizing these properties in a big giant list, it's great to have some basic understanding of what these properties mean. In order to come up with that understanding, a good way is to always go back to your unit circle or your SOHCAHTOA, like the really fundamentals about sine and cosine, in order to understand those functions a little bit better. All right, thanks for watching.